All right, Stuart again. Today we're going to have a little talk about distributed data and some considerations for it. So here's the problem statement. As I worked with my enterprise customers, we often have to have geo-distributed data, or at least data that's distributed over multiple data centers. And this is outside the normal high availability data this is outside the normal high availability disaster recovery and business continuation. This is scenarios in which data is coming into multiple data centers around the world, and we need to have a strategy for dealing with that. And I'm going to hit some of the things to talk about in that area. So a couple of things is fundamentally, you've got to consider a different set of problems when you're designing schema that is going to span geography. And we'll talk about that. And the more sources of data you have, the more complicated the sources of data have, the more different places data is coming in, the more important management of data becomes. And that involves essentially really biting down hard on data governance and stewardship and paying attention to master data management and having data ingestion pipelines that understand and respect some of the challenges we're going to talk about. Critically, one of the areas that I've seen cross-geo data collection fail is that organizations are of the mindset that their operational data, analytical data don't have to be separated from the onset. And that causes an innumerable series of problems. And so we got to consider a different set of considerations and complexities than we would if we were building something for the cloud that's going to fundamentally run in a single data center or a single geographic region. If you know that's going to happen, then you have to invest time ahead of the project to think about it. It's really hard to fix a bad data model after the fact. And this is above and beyond the normal domain-driven design considerations. And when those are reified into storage, which are semantically and operationally separate areas, right? That we have a process that we live in every day to deal with it. You cannot get a year or two into a project and suddenly realize, oh no, my geographically distributed data is not going to be happy. And I need to do a huge and probably painful and potentially dangerous and lossy retrofit. So we want to come to a place where even the thought that this might be a requirement is tackled right from the offset. So in this presentation, I'm going to consider two styles of data intake and data design. One is sort of batch-oriented data that typically we think of in traditional data processing, and that is we're going to have aliquots of records coming to us, either operationally through the software, or we're getting data from the outside, and the outside could be just anything outside our system, right? Could be other actors, other organizations within our own enterprise. It could be data coming from partners. It could be data coming from third parties. It could be data that you're purchasing, but essentially batch-oriented data. And the other kind of data we're going to talk about is stream-oriented data, and we'll get to that in a few minutes. Any kind of data processing pipeline of any complexity at all has got a lot of things that need to happen for that data to be sanely incorporated into the operational data set. And then that's repeated when the operational data is digested into analytical data sets. And so for a long time, I've been of the opinion that ETL is basically in the wrong order. And I'll explain that in the diagram that's coming up. But fundamentally, we want to get the data loaded into an in-memory or other structure within our database engine. Call it, raw data tables or staging tables or, preloading tables or whatever. But fundamentally, the first step in the journey needs to be getting batch-oriented data into the engine so that we can do set operations on it. Because if you're using a relational database, set operations are the strength of a SQL-oriented database. But the same is true for example, for NoSQL databases, document databases that might store XML or JSON. Getting them loaded into a format where a set of incoming data, let's say it's a bunch of JSON data or XML data, and we load that into this place over here in the NoSQL engine we're going to be using. Then we use the power of the graph engine in the NoSQL database to do things that we need to do with our data. And it's also true for data that is essentially unstructured, right? We want to get it into a place where our tooling that has all of the nice features that we want can come to grips with it. So for unstructured data, for example, you might want to load it into distributed storage so that your Hadoop engine, for example, can get to it. And the other thing is, particularly if you're getting data from a bunch of different data sources, and this is magnified if those data sources are coming at you all over the world, and where they need to land is in different geographies. So why would that happen? Well, we might have GDPR concerns. Data for Brazil needs to stay in Brazil. Data in France needs to stay in France. We might have agreements with the people who supplied us the data. We promise to keep your data in these spots and these spots only, except for a list of exceptions. Typically audit logging, operational procedure logging, and some agreements about non-attributable summaries of data. That is to say, the summary can't be used to recreate the original data set. And there are lots of rules. And if you're new to that, you should probably consult a data scientist or a professional data engineer, and they can tell you all about that. And there are statistical tests that you can use to prove whether or not you're rolling up or sampling or aggregating the data in a way that's okay. You might have internal compliance teams that have similar demands. No matter from whence the demand comes, though, we have to do our data processing in the main for Brazil in Brazil, for France in France, for North America in North America, and so on. So getting the data preloaded into some place our engines can get to it and do useful things is a good first step, because it enables the next thing after the data is loaded or staged or whatever you want to call it. And we can start a data processing pipeline, a variety of kinds. We can do two really important things. One is we can version the data. That is to say, we can give it additional metadata about each batch of data as it comes in, so that we have the ability to build an audit trail. And somebody says, where did this fact come from in our analytical data source? We can trace its entire lineage backwards and say, well, this fact originated from import number 27B from using this version of this data processing pipeline from this exterior source on this date and this time is when it started processing, and it stopped processing at this date and this time, and all the other metadata that we would need to have the ability to demonstrate that our data flowed uncorrupted. That doesn't mean we didn't enrich it. It just means we have proof of the original set. And furthermore, if it turns out we have a bad version of the data, we had a bad file, or we had, we made an operational process change in our data processing pipeline, or somebody else made a operational change in their data processing pipeline, and the next batch of data you got from them was, well, not good. Having the ability to attribute rows in your data to where they came from and how they got there is incredibly useful in case you ever have to back them out. And in some systems, backing out is not allowed, but from the original batch, you can then construct a compensating transaction that effectively adjusts the bad data out of your intake. And then you can ask questions about, what did this data look like in time? So for any kind of data that's in batch, and in fact, if you have a user interface, right, and you have users industrially typing into it, from the scale of time, those things really are just batches. And what differs is the cardinality of the batch. You might only be getting one graph at a time, right? One domain-driven design root graph, which they call an aggregate, at a time. But it's still a batch. It's still a group of data that's going to result in being enriched and transformed and ultimately updating your operational data set. This is an incredibly simplified, not untypical flow. And there are lots of examples of way more complicated things than this. But this outlines the basic strategy that's generally applied to dealing with data in batches. And particularly if you have a UI system and that UI has got an API facade and your services are all in service of a particular domain, you're going to have data flows that service that domain as well, and potentially send updates via DTDs or messages or something else to other domains that might have a shared concern. It's important to have a data processing pipeline that can accommodate that. So we start with raw data, and I have a file symbol for it, but honestly, it could come from anywhere. It could come over the wire as a data transfer object from an API or a UI. It really doesn't matter. It could come from a CSV file. It could come from a JSON file, an XML file. It really doesn't matter. What we want to do, though, is we want to load it into a table. And I'm going to use the language of SQL as I talk about this, because I'm a relational database person, although I use NoSQL and storage-oriented databases like Azure Table Storage, things like that. I just picked the best tool for the job. But conceptually, you can think of a table as a set of related data where the rows are data instances and the columns are, each one has a semantic meaning, right? This is the ID column. This is the first name column, right? So I'm going to use a tabular context. But honestly, if you think about it, this works with graphs too. It's just that tabular data is a graph that is only one deep when it's loaded out of the file. Although if it comes out of XML or JSON, it could actually be a fairly complicated graph. But the upshot of all this is that you want to load that data into your engine or a surrogate for that engine, like engine adjacent storage, with no transformation at all of the values or the semantics into a place where you can then do things with it. And again, I'm going to use the language of SQL, but really it applies to anything that is a set of related data that you can operate on as if it were a graph or a set. And I'll argue that graphs and sets are interchangeable with each other, with the exception of a few special cases that rarely show up in business scenarios. So the next thing we want to do is we probably want to tear that raw data up into tables that, or storage locations that represent the entities that are in the aggregate. That is to say, you might have order, detail, and a pointer to product. So you probably want to break those up so that you can start consolidating those. And depending on what the ultimate storage engine is, they may end up in the same place, but you may want to break them up so that different parts of your data processing pipeline can do different enrichments and different validations and so on. Fundamentally, that's the idea. The orange tables are where we actually start to modify data. And we keep modifying that data by doing transforms. In the relational databases, we're typically creating primary key, foreign key relationships. We're typically checking constraints. We may run a set of rules on the data, but we're going to be doing set-oriented operations. In a NoSQL database, we're going to be doing graph-oriented operations. And in a storage-oriented system, we're going to be doing validations and enrichments as the result of the execution of a chain of functions. But morally, I'm just going to say those things are all equivalent. They just have a different mechanism. Fundamentally, we're decorating, modifying, and increasing our graph. And depending on your engine, you may be splitting that graph into pieces. And then at some point, that data is deemed worthy, and it flows into our operational data store in green. And as we do that, right, we have invisibly to this diagram an audit trail that's going to live for a long time. And that audit trail is going to have that exterior identifier of a batch and its metadata so that we maintain lineage. And generally speaking, it's a good practice to put the batch identifier in to the green tables as the result of manipulations, inserts, updates, and deletes. It's also a good practice not to do hard deletes in these scenarios, to have a soft delete column. Because then you can say, well, this row was deleted as a result of an action that came from this batch. If you have a hard delete, then you have to wander back through your history table. That may be a valid strategy, but what I'm saying is data shouldn't just disappear, right? You should have a way to bring it back. Our axes, invisible to this flow, are this idea of a batch identity and its metadata, and a running and persistent audit trail that we're going to hang on to as long as we hang on to the data. In other words, the data retention policy applied to the rows themselves that end up in the green should apply exactly the same to its audit trail and batch info if you want to have the ability to do data lineage properly. And by the way, storage has gotten cheap. So, you know, if you have a tertiary process by which data goes through its data life cycle, which includes how long it's going to be retained in the operational store, how long it's going to be retained in the archival store, and then ultimately when the data is going to be destroyed, if you have the discipline to do that process, then you have the ability to retain the batch and audit information at the same time. So that's a consideration. We're going to talk about key design in a little while, but that's also a consideration. Contrast that with stream-oriented data. And when data processing first started, stream-oriented systems were rare. They didn't not exist, but streams were often broken into batches. The sensibility now in the data processing community is that streams have fundamentally different life cycles, and they have different operational procedures, and we may not care about the individual data elements as much as we do about some aggregate about them or some metric about them. And a metric is an aggregate over time, right? If we're going to talk about metrics, we're always talking about the time dimension. So we may be getting diagnostic streams from manufacturing. We might be getting, logs from servers. We might be getting system events. We might be getting business events. Like we have a new carded order. We have a new carded thing. The carded thing got converted into an order. The order went to be bursted into suborders by distribution channel, et cetera, et cetera, et cetera. And those are interesting. We may have situations where during the business process, we said we needed to communicate between different parts of an overall domain-driven design. So we might have, dozens of domains, some of which, as the result of data processing or just computing in general, we may need to tell them about this thing happening. So we're going to need to process those. And you may have situations where you have a system like a trading system or a bidding system or some sort of tracking data system, and you are going to be getting these continuous streams of data, and you're going to be making decisions operationally, but also in the business context about what your overall processing is going to look like as a result of getting in these streamed things. And for the sake of, again, vocabulary simplicity, we're going to call each of these atoms of things a message. Now, they're not all messages, all right? But message is a handy thing to hang it on. And in lectures where I've used the word atom, people tend to get a little fluffed. You can see I actually pulled some of this from a presentation I gave at a conference, and I still talk about atoms. But a lot of people, if you say, oh, we got a message from the XYZ, milling machine that, it had started the processing of this thing, or that, it's one of its cutting heads needs to be replaced or whatever. It's still, they're messages, right? And there may be grouping, right? So in the case where I have a factory, right? And it's got all these different CNC machines. The grouping may be, oh, all of these messages came from the same CNC machine, or even more nuanced. All of these messages came from this CNC machine running this job type, right? So it might be making, one thing about CNC is that one day it may be making part A, and the next day it may be making part B, or maybe during the course of a workday it makes 7 different parts, depending on what the supply chain looks like. And supply chain is a really good word because it describes something about data processing too, and that is, as I said in the last part of this talk, we really want to have a sense from where our data came from and what it got used for. And you can call that the data value chain. You can call that, you can put relevance on those things. You can put business value on those things, right? Data processing can be looked at from a number of different angles. But one of the angles that for sure is going to be useful is this idea of where did our data come from and what did we end up doing with it? So it's good for each of these messages, atoms, whatever, to have a unique identifier. That unique identifier can be a composite, right? We can say, well, based on these 5 fields, we know it's unique. So based on the combination of factory, subassembly, area, CNC machine number, job type, and event type, we have, and, date timestamp, we have a unique message identifier. Perfectly fine. Usually when we're dealing with stream-oriented data, we want to get data out of the stream. That's really useful. And fundamentally, it falls into two sort of thought areas. One is the obvious ones, which are aggregates and metrics, right? We want to get the, the minimum amount of time it took to make this particular part for this assembly, the maximum amount of time it took, what was the average, how does that change over time, right? So when we add time, we start getting a metric out. You may end up be doing something called selection. Selection being the opposite of projection, right? A projection is, I have a set of data, I want to make a tabular thing or a graph that extracts elements of that data. Selection's the exact opposite. So for example, if we have a system that keeps track of parts availability and we're getting parts in the door, but they're at different price points from different manufacturers, we may need to steadily recompute the price. If those parts are being offloaded into products, right, where we're assembling the parts to make something, then, we may care about, the quantity, because the quantity and the quantity use over time allows us to project our real physical world supply chain. If we have an auction system, then we need to keep track of who's currently the winning bid, because that's a useful piece of data and what the price is and some other things. We may want to have a way of detecting data that's out of the ordinary. So our CNC machine says, I am broken, or my tool heads are kaput. Or we may have a business system component that says, you know what, I've been getting a whole bunch of 500 errors and I am almost non-functional. Or anything else about your domain that is an unhappy path. We call that being alarm worthy, e.g. you should be alarmed. Sometimes aggregation is the purpose of the whole stream, right? And the actual data is archived almost immediately. But sometimes the data can be ensorcelled into operational stores if it updates or affects other records. So let's take a look at one of those typical flow scenarios. This one I just threw the kitchen sink at. This is every possible thing that you could do. So typically we're loading the messages raw into some store. We have some process that might do some enrichment, and so you get, you go from message, of bare metal message to message with additional metadata. So we might replace the CNC serial number with something a little more human useful or whatever, right? And there can be lots of these enrichments. Typically these things are handled as a pipeline. So as messages flow in, your pipeline, which works in near real time, is going to be, enriching and validating and making decisions about messages. And then we may use an aggregator. That's what that next symbol is. And we may, from there, produce metrics. We may need to from those aggregates, we may need to pull out who's the winning bid. What's the balance of your bank account? What is, what is the state of a CNC machine? Is it in the idle state, the happy state, the unhappy state? Right? Is it working on something? Is it broken? Is it off? Those are all reconciliation things. And then just straight up ingestion, right? And that's, I got this message and now I need to do an update on this record because I have a status change for something. So, my fulfillment domain may tell our order customer service domain that the fulfillment pipeline has, for this suborder, has it ready to ship, or that it's shipped, or that the shipment will be delayed because they couldn't fill your order or whatever. And then ultimately you're going to end up putting the raw messages into an archive. You may put the enriched messages into an archive instead. In that case, you want to make sure that your enrichment is non-destructive. That is, that I can do a projection on the enriched message and get back the original message with some surety. And again, invisibly to this is the idea of an audit trail and idempotency and the ability to maintain a lineage to a particular piece of data, particularly if you're doing reconciliation and ingestion. But even if you're just doing metrics and you have the ability to attach metadata to those metrics, knowing what caused that metric to change will allow you to look at the metric's history over time and go, this was a really weird peak or valley, and drill into it and go, oh, we were getting some funky messages out of, Fab's sub area 8, and that's not okay. And maybe we should try doing analysis that excludes that area because maybe there was a malfunctioning piece of accretion hardware that was collecting these things and turning them in from sort of an analog state into a digital state or whatever the accretion appliance does. And so it's useful, right? And you may not do all of these, right? You may just do some of them, but this is not an untypical flow where we want to use stream-oriented data to get something done. But again, the fundamentals of being able to have attribution is critical, as well as the audit trail of who did what processing to this piece of data and why was it selected for a metric, why was it selected to participate in a reconciliation, ingestion, what have you. Which brings us up to governance. DAMA, the Data Management Association, defines the process as this. And reading a bunch of different sources on governance areas, the way that you get 3 opinions on data governance is you have 2 data governance people in a room. So I tried to collect 10 things that you should at least think about as you build out a governance program for your data. And it's especially important when your data is geo-distributed because without governance, you don't know how to deal with exceptions. You don't know how to properly and formally make changes to data processing pipelines that might need the same logic in different geos, or they might require custom logic in different geos. And how do we regulate that? How do we ensure that our data is secure? How do we make sure that somebody cares about our reference and master data, what I would call lookup data? What is the governance around building out business intelligence artifacts, data warehousing, data marts, data lakes, data oceans, whatever you want to call them, right? But we got to have some rules for that. They have to be audited. How data got into them, what happened to them, who saw it. And then we just need to know a lot of data about the data, right? We talked about audit trails. We talked about batch numbers or, other idempotent, useful identifiers. Somebody's got to manage all that. Someone's got to care about the data quality. How do we know our data is representative of the reality we expect? When we have variances in that, is that a change of circumstance to which we should pay attention? Or is something gone horribly wrong and we may need to be able to reprocess the original data through an amended data processing pipeline? And if you don't have the ability, whether streamed or batch, to go through and send the same data through a different data processing pipeline in order to amend something that has gone horribly wrong, you're missing out on an area. And the more geo-distributed your data is, the more often this will happen because the complexity of your data processing system by definition has gone up when you have geo-distributed. And obviously, domain-driven design, data modeling, choosing the tooling, choosing the governance around that tooling, training in that tooling, the appropriate compliance processes, the ability to prove to either the business or contractually or legal entity that is your regulator on the outside, that you have followed your own process, is critical to success. Which brings me to my pet peeve. Master data matters. So we talked about lookup data, and a lot of it really gets treated very badly. Somebody somewhere, usually a developer, says, we probably ought to have a lookup data that has all of the milking machines broken down by the dairy. Yeah, all right. But that's where it ends. And all the things we've talked about, auditability and lineage and things, get ignored or worse. And I've seen this happen over and over and over again. Data with the same semantic meaning needs to come from one source of truth and have one advocate. So if I am dealing with, and here's the infamous one, customer, my customer in division A and your customer in division B may be different, but the same legal entities, right, whether that's a person, a corporation, what have you, need to have the same semantic meaning. So if someday the people above us in our program or our project go, I need to understand what Foucault has done across our various offerings, you have that opportunity. And for common things that you can find an external source of truth for, right? You really need to get together with all your peers and go, let's agree that while we may want to enrich for our use in our system this core set of data, that we are going to collaborate on curating this data set. We'll have change control on this data set, and we'll make darn sure that we use sane, effective dating so that we can do reporting and analytics as of a particular period of time, and that as the data changes, our systems, who will pass in the appropriate date when looking up something or getting a list of something, can specify. And if they don't specify, we assume right now. Although you may want to enforce people explicitly saying, I want this data as of right now. Depending on how fluid the reference date is, that might be pretty important. And I'll bring up the soft deletion thing. Never reuse one data element for a different set of semantics than its original. It needs a new name. And by name, I mean a unique key where the semantic are well understood. So if Foucault breaks up into Buco and Guco, then in our data lineage, we should see the breakup of Foucault and Duco, and we should see a back reference in time to Foucault. And now we have two new legal entities, Buco and Cuco, and as of a certain date, the separation was complete, but the lineage is preserved. That requires discipline and coordination, and it's time consuming, and that can be very aggravating to people who want to just get in it and go. But again, the more geo-distributed we are, the more complicated they are. The more actors we have in our governance process, the longer things will take. It's just a law of human communication. And not having enough time isn't a good enough reason. And you've probably heard the famous phrase, people don't plan to fail, they fail to plan. And when it comes to master data, that's absolutely what happens. So reference data, as an aside, can be really complicated. We could say, okay, we're going to use ISO 3 codes for country because they come from the International Standards Organization, and they have as of dates, they have unique identifiers. They do not reuse the same key value for things with different semantics. So if country A and country B divide, or country B and country C form country A together, right? History happens. That's trustworthy, but we are going to then need to enrich that with potentially jurisdictions. If I'm doing reporting, right, of my business activity to one of my regulators, we're going to have to define an entity that is either bigger than a single country like the European Union or smaller like one of the states in the United States. And so you would think that you could get together and agree that those jurisdiction trees are fundamentally the same. But in fact, it turns out that this is where things start to come unglued. And it's fine until System A and System B have to exchange data in which that entity, jurisdiction, is a participant. And then we'll wish that we had maybe gone back and said, you know what? I can see this coming. Country is not sufficient. We need a way of classifying aggregations above country and disseminations below country in a way that has effective dating, that has unique semantics for each row, and that we can agree on as an organization. And if we have a conflict, then we make sure that we understand hierarchically where this happens. And if we have a complex aggregate, like a jurisdiction crossing two geographic boundaries, for example, we have a United States state, California and Nevada, and they have a jurisdiction jointly for firefighting or something, that we have a way of handling that within our data model. And that requires sitting down and thinking about the domain and then building a data model that supports the potential semantics of that domain in a way that's performant, efficient, audited, idempotent, and consistent. So we should talk about considerations for key design. It's bad enough if you've only got one instance of a database in one place. But when you start getting things that are geo-distributed, it becomes even more complicated. So our favorite keys are keys that come from the outside. So ISO keys or IPSC keys, that's International Postal Society, I don't know, whatever. It's the International Postal Agreement, right? If you can find an outside vendor of master data that you can grow on. So if you're trying to keep track of corporate entities, right, you could use Dun & Bradstreet or whatever. But things that come from the outside as natural keys. Now, those may not be the primary keys of your SQL table or how you organize the documents in a NoSQL database or the partitions in a tabular store, but they exist in a way that's traceable. And so we can crawl back through the data using the data processing pipeline and figure out when we have inconsistency. The next best is if you can get together as a corporate or entity, or at least a greater division entity, we're the government reporting branch, and say, we're going to have a source of authority for certain things. And everybody's going to use it. And if you go to use it and you find that your thing is missing, here is the governance process to get that addressed. And here is the SLA around this process. And so on and so forth. Who, at any one time, I should know who I need to talk to say, look, we are missing an AR billing code, and here's the thing. Like, how do I get this introduced into the master data source so that the next time I go to use it or I replicate it because I might need to geo-replicate it for efficiency, then, how do I get this introduced? The next best is see if there's an obvious composite key. And again, we're not stipulating that these are the primary keys or the partitions or whatever. We are saying that composite keys can be uniquely used to identify rows, documents, sets, whatever, in a way that's computable so we can crawl. Relying on central key servers is often a useful strategy. And it's kind of a riff on the source of authority pattern, but you have something that just hands out keys. I'll point out that when I first started doing data processing a long, long time ago, this was really the only way to do this. But now we have cryptographic things like GUIDs and nonces and other surrogates that can be used so that if I add a record in Europe and you add a record in North America, that they don't collide in identity. And this is not easy, right? You've got to think not only about the domain-driven design considerations of entity representation and relationship, but you also have to consider the fundamental data processing pipeline problem of how do we get this in a form that is going to make sense if we need to aggregate the data across, that's geo-distributed. How do we make sure that somebody didn't decide to insert the same darn record in the European Union and Canada? I've seen it happen. So how do we find that? Or better yet, how do we stop it? Right? Things to think about. Lastly, I'll leave you with my favorite quote of all time. And this is Segal's law. It dates from 1904, so it's a little less than PC, but it does describe perfectly what we care about fundamentally as we think about distributed data. And that is, a person with one watch always knows what time it is. A person with two is never sure. Thank you for your kind attention.